And there we are. Okay, we're all set to go. Good morning, everyone. There's a couple of things I wanted to do today. So I want to go through chapter 12, which is pretty short, but I just want to show you how we can use Sage to do some quick calculations now that we have this idea of a group defined. We can see how we can implement groups in Sage and have Sage tell us a lot of stuff about our puzzles that we may or may not have known we could get it to tell us. And then once we've got a little bit of play in with Sage and our puzzles, then we're going to go into chapter 13, which is starting to come up with a systematic approach to understanding all sorts of puzzles: Rubik's Cube, oval track, pretty much any puzzle, any twisty puzzle, any permutation puzzle. These are going to be the start of the development of the tools that will help us solve them, do solvability analysis of them, so criterias, and develop move sequences, etc., understand the theory. So you may say, well, why is it just starting now? So all of the previous stuff on permutations, they form the building blocks of the groups. So a permutation group. Now we've got the ability to work with permutations and orders and their structure, and then we've now encompassed them in this idea of a group. And now we're going to take that and start to analyze puzzles with it. But there's two fundamental tools that we need in order to move forward, and that's the idea of commutators and conjugates, and that's chapters 13 and 14. So you're going to see very quickly today that we actually know how to do a lot of stuff. We can just tease it out of what we've done so far, and I'll show you how to develop some nice move sequences on the Rubik's Cube that could do some small moves and maybe help you be able to solve it at this point in the course. So let's get started. So first definition: permutation puzzle, just so we are able to take an object and say, is it a permutation puzzle or not? Can our analysis and tools apply to it? So a permutation puzzle is a one-person game, also known as a solitaire game. And this is in contrast to a two-person game. So when you hear the word game theory, typically that refers to two-person games, two or more persons. And so that's not what we're doing here. We're doing one-person games. So you can call this puzzle theory if you want, with the idea that it's just related to a single person and their wit, their skills against the puzzle itself. Whereas game theory is about the dynamics between two different players and how they sort of have to understand and analyze each other's strategy. So we're dealing with just one-person games or puzzles. And what a permutation puzzle is, it consists of a finite set of objects, and namely the pieces of the puzzle. And there's four properties. So depending on the puzzle's construction, each move, which that's the depending, each move is, well, what you can do with it depends on the puzzle's construction, but each move is a unique permutation of the numbers in your set T. So for the Rubik's Cube, if we label the 48 stickers, excluding the centerpieces because they're not moving around, but if we label the 48 stickers, then every move is a permutation of the stickers. If the permutation corresponds to more than one puzzle move, then the two positions reached by those two respective moves must be indistinguishable. So what that means is, you know, let's say on the 15 puzzle, for example, we had a 3-cycle we wanted to achieve, and this is, you know, most easily illustrated through the midterm problem. Was I got lots of different solutions, all of them fixing the 3-cycle, but there were a lot of different move sequences that did the same thing in the end. And so that's the idea with point number 2, is that you can achieve the permutation by doing different move sequences. But all that matters is the end permutation. So whether you did your 3-cycle using 24 moves or 50 moves or 100 moves, it doesn't matter. All that mattered is you did the 3-cycle. Okay, so if you can, if you can achieve the same permutation by doing it in with different move sequences, then the resulting configuration of the puzzle is indistinguishable between those two different move sequences. The same permutation was done, the same configuration was achieved, in other words. So number 3, each move must be invertible. So if you do a move, you should be able to undo it. And here the move means move sequence. So if you do a sequence of moves, you should be able to do them in reverse and invert them and get back to where you started from. So there's inverses. And number 4 is if you do a move sequence and then you follow it by another move sequence, then doing the 2 move sequences back to back is equivalent to multiplying the 2 permutations that you got for the individual move sequences. So this is really where the group structure is coming in. There is an ability to multiply move sequences. That's part 4. Each move sequence has an inverse. That's part 3. And there's basically a do nothing move sequence. You don't even have to touch the puzzle. That's the identity. And so there's where our group structure is coming into play. So we're going to let PUZ or PUZ denote a permutation puzzle. So it's either going to be like the Rubik's Cube or the Oval Track or the Hungarian Rings or any other puzzle that we're going to consider. And we're going to, from this point forward, we're going to consider puzzles without gaps. So unlike the 15 puzzle. So we're going to consider puzzles that don't have any gaps in them. This was actually one of the things that Erno Rubrik commented on about the 15 puzzle, was that didn't like the fact that there was a gap in it. Whereas the Rubik's Cube had the nice property that when you twist it, you get back to your cube-like shape again, and there's no gaps that's sort of sticking out at you. And so that was one of the aesthetics about the Rubik's Cube, was there was this nice feature that it didn't have any gaps. The moving parts didn't have to do with the fact that there was a piece missing and things were sliding into its place and the gap was moving around. So we're going to let M PUZ, so be the move sequences of the puzzle. So these are all the inequivalent move sequences. So these are basically, you can think of these as all the possible configurations of the puzzle, because 2 move sequences are equivalent if they achieve the same end on the puzzle. So basically you can think of MPUZ as being all possible configurations. So I've written there 2 moves that are considered equivalent if the 2 positions reached by these moves are indistinguishable. Then what we have is that the set of all these move sequences on a puzzle is called the puzzle group. And that's the group we're going to be assigning to each puzzle as we move forward. Today, with this section, we're going to see how we can do these things in Sage. These are all going to be, as we said, permutation puzzles. So let's see how we can do them in Sage. So I'm not going to follow the notes now. I'm going to pop over, but I wanted the notes there just as sort of a backbone so you can see what we did today. I am now going to pop over to the Sage window where we can actually do some computing. If you want access to this sheet, these any of the Sage sheets that I do in class, just looking up our course website, here we go. Let me just bring it over so you can see. So under our lecture schedule, if I scroll down, puzzle groups, you can see the code from the book. And this is basically what I'm doing here. You can view it in the browser window, or you can download the IPython notebook and then dump that into your own space in sage.syzygy. And then once you've done that, then you can feel free to interact with and play with the notebook as we go along. Okay, so what we're going to do is we're going to start building these puzzle groups. So for the Rubik's Cube, this is our first one. I'm going to label all the stickers from 1 to 48, much like we've seen in the past. And so I'm going to build the Rubik's Cube group. Inside the symmetric group, it's going to be a subgroup of it, because not all permutations of the stickers are possible. And so we'll label the permutations corresponding to the moves, R, L, U, D, F, and B. And then this is where we needed the idea or the notions from chapter 11. Now what I'm going to do is I'm going to build the subgroup, which consists of these 6 moves, R, L, U, D, F, and B, and all products of them and all inverses of all products. So we're looking at the subgroup generated by the 6 basic moves. So this is the subgroup generated by the 6 moves, 6 basic moves. And I'm calling that RC3, Rubik's Cube, the 3x3x3 case. And so I've just, couldn't really see what I did, but I have my cursor in the window and I do a Shift Enter. And now you can see that this highlighted box now comes to the next execution cell. That means now I've stored in memory, I've stored RC3 to be this group. What can we do? Well, there's a few things we can do, but what I'm going to do first is I'm going to say, how many configurations are there of the Rubik's Cube? That is really just asking, how big is this group? And so I can ask for how big the group is. What is the order of RC3? And there it is. That's our 4.3 times 10 to the 19. And we could factor this. And so basically the way this is working is this is a group. And as a group, it's got an order method associated with it. So I take that method and I take RC3 and I hit it with the order method. That returns the order. Now this is an integer. And because that's an integer, I have a factor method on integers. And so I can dot factor it. And so when I factor it, I get that factorization, which I used last day, 2 to the 27, 3 to the 14, 5 cubed, 7 squared times 11. And so that's how big our Rubik's Cube group is. That's all possible configurations there are of the Rubik's Cube. And there it is in factored form. Okay, so that's the first thing we can do. We can very quickly find out how many configurations there are on our various puzzles by introducing them in this way. Other things we can do is we could now ask questions about whether certain moves are possible. So the 718, that's an edge flip. Let me just drag this out of the way. 718, grab my pen. Where is that? 718, that's this here. Maybe I'll put it in pink. That's asking, can I swap the positions of those two stickers? So that's really asking, is an edge flip possible? So I go ahead and I ask, this is a permutation in S48. So this is in S48, the full big permutation group on 48 objects. I want to know, is it in this subgroup, RC3? And it comes back telling me it's false. So no, I can't flip an edge. Okay, so we are going to do all of these things by hand eventually. It's not going to be a tedious calculation, but we'll see how we can do these things. In fact, we already knew we couldn't flip an edge. We already did that by hand by a parity argument. But other results that we're doing here, getting with Sage, we can do by hand, and we'll do those later on. But I think it's important to show you this now, because if you're wanting to analyze a puzzle for your end of term project, you can already start to gather information by using Sage and querying it with different problems. You just set up your puzzle and then you start asking it different questions to see what's possible and not possible. And then you can back those results that Sage give you up as we start to unroll the theory a little bit more, and you'll see why certain things are possible or not possible based on our theory. And we've already seen that for the Rubik's Cube and the midterm problems. You already know how to check to see whether you can swap 2 corner cubes or 2 edge cubes or flip an edge cube. So some of these things we've already seen before and how to do them by hand. Now, what's this next one? This is asking, can I flip the 718 and can I flip 526? So that's just another edge cube, 526. So it's asking, can I do a double edge flip? So maybe double edge flip possible. That's what we're asking here. And so we'll execute it. And true, yep, it is possible to flip 2 edges. It is possible to flip 2 edges. So that tells us it's possible. It doesn't tell us how to do it, though. So that's one thing to keep in mind, is that this is not telling us how we can do this double edge flip as a product of the R, L, Ds, Fs, and Bs. But it does at least tell us that certain things are possible. And now it's motivating us now, okay, let's figure out how we can do it. One other thing I think is kind of fun, Sage does have a built-in cube solver. It was written by David Joyner. And it's, you call it by, first of all, you call the cube group, and I've just called it Rubik. And then you can call these names R, which is the R move in Rubik, and so on down the list. And then you can do things like multiply and whatnot in it. But we can already see how to do those multiplications up here. We want to do the reverse. We want to, given a permutation, figure out from that state what is the solution. And so let's just run this and see how it goes. So there's the sequence. It tells you if you turn the front face 2 clicks, the right face 2 clicks, an inverse back move, so a counterclockwise click of the back face, a counterclockwise click of the front face, and so on, that you can do the double edge flip. So this is just a fun little thing to note that, yep, Sage Math does have a built-in cube solver. So our mathematical software package does actually have something puzzle related already built into it. We're not going to use this at all, but you might. I mean, we're not going to use it in class, but you might just have some fun playing around with it. Okay, so what's next? Let's go to the 2x2x2 Rubik's Cube. So that's this little guy here. And there's no centerpieces. It's basically the original Rubik's Cube with only corner pieces. Oops, I'm off the screen there. Only the Rubik's Cube with just the corner pieces. We could do the same thing. We could throw it into Sage. And here I've done RLUDFB, and I'll execute it. And then I'll ask for the order. And there's the order. There's about 3.5 million configurations of that. Now, you may look at this and say, wait a minute, you didn't use all the moves. I just used right, down, and front, just a twist of the right face, the down face, and the front face. I didn't use the left, the up, or the back face. Why didn't I do that? Well, let's see. If I do that, if I use all of the moves and store that as H, and then I ask for the order of H, I get a different number. Why is that? This is doing all of these possible moves, all of the 6 basic moves, forming the subgroup of them, and I get a different answer than just doing RDF. And so which one's right? Really, I should be using all the moves, right? I am overcounting. Yeah, exactly. R and L are the same in a certain sense. Same with the up and down, exactly. So there's some redundancies here. So let me just bring across what I've actually done. Where's my 2x2? There it is. So if I do a right move, maybe I'll hold it with the yellow face to the side. So if I do a right move, that's the configuration I get. But, so notice that that now has blue next to red, and then red next to green, and so on. So that's a right move. What if I do a left inverse move? I actually get the same configuration. So in other words, what I'm doing is I'm noticing that if I do a right move, that's the same as doing a left inverse move. The only difference is what I'm staring at on top, but the puzzle configuration is the same. Or another way to say this is if I do a right move, I could solve the puzzle by doing a left inverse move. Or maybe I did the left inverse in the opposite direction. Sorry, I'm trying to stare at too many things at once. But that's probably a better way to say it, is if I do a right move, then I can solve the puzzle by doing a left inverse move. And so a right times a left inverse is the solve state puzzle. Right times left inverse is solved. So R is equal to L. And that's what was stated in the comments. R and L are the same, exactly. So we don't need to include the opposites of R, D, and F because we're getting redundancies. Okay, so that, you might say, well, that doesn't make any sense though, because this, I mean, it should detect that. If R is the same as L, then it should detect that and it just not count that as a different element. Well, the thing is that by different, Sage is doing something by treating R and L as different than what we would do. So I'm going to again bring this back over here. And we'll look at this again. Now remember, our numbering is on stickers. So I have to fix an orientation in space. So this, let me say this, this one's number 1. So that blue sticker on the red, black, blue corner, that's number 1. This is number 2. This is number 3, and so on. So if I do this, if I do a right move, followed by a left inverse move, the puzzle is solved. But this isn't the identity permutation, because what was here was this one. So 1 has actually gone back here now. So this is not the solved state in terms of a permutation. There's a permutation associated with this. 1 has gone to the back, and basically all the stickers have moved to different locations. It just so happens that it's solved. So this is one of the things that the 2x2x2 Rubik's Cube has that the other one doesn't. And why is that? Because in this, for this Rubik's Cube, our moves are just our side moves. This blue face is always on top. That blue center is always on top. So if I did a right move followed by a left inverse move, which is basically what I'm doing on the 2x2, I get this, but that's not changing the orientation of the cube. Blue is still up top. Whereas with the 2x2, I'm changing the orientation of it. So what happens here is I'm actually able to get different symmetries of the cube. You know, if I want to know, doing cube moves, could I rotate the whole cube, let's say about this diagonal axis? So I want to rotate the whole cube like this. Could I do that? That's a symmetry of the cube. Could I do that using cube moves? Well, that's going to put blue face on the right side and black face up top. So I can do that. I'll do it using cube moves. I'll first put the blue face over on the side, doing cube moves, and then I'll put the black face up top, doing cube moves. And there we go. So I'm able to achieve symmetries of the cube using cube moves. That's what Sage is detecting. It's detecting that the cube has changed orientation. And so when I realize that, I say, okay, this is the actual size of the group, the 3.5 million. What I've computed here is actually a bunch of different orientations of the cube that are all in the solved state, but it's been rotated. And so what that means is I would expect that the order of H divided by the order of RC3, or how much I overcounted by, is the number of symmetries of a cube. And so when I do that, I see I get an answer of 24, and those are precisely how many symmetries there are of a cube. Yeah, exactly. This is like the dihedral group. Yeah, there's rotations going on here as well. We're not accounting for reflections, but yeah, there's rotations going on here, and we're able to get rotations through cube moves. Whereas I can't get rotations on the 3x3 cube, right? I could never, so again, I'll start with blue up top. I could never get a rotation on the 3x3 cube that does this, that moves the red up top through cube moves, because cube moves just move the faces. So it's never going to bring that blue sticker, that center blue sticker, to the back. The only way I can do that is I'd have to actually physically rotate the cube, or I'd have to allow for slice moves, these middle layer moves. But to do a slice move, I could really just say, well, all a slice move is 2 of these face rotations, and then a whole cube symmetry, a whole cube rotation. And so we can not have to worry about those sort of whole cube rotations coming up in our Sage calculations, because we're only using the R left, the right, left, down, up, and front, back moves, and those don't move the centers. Whereas with the 2x2x2 cube, we can get those symmetries. So that's just one thing to notice, that I had to cut out a couple of the moves because of overcounting. Okay, let's go on and have a look at the next puzzle, the oval track puzzle. So this is our, oh, sorry, you couldn't see that. Oh, darn it, thanks. Yes, here I am doing something and can't even see it. So the idea was for this blue sticker that's on top, how can I get that to the back? Well, I have to fully rotate the cube. So I have to use symmetries of the cube to move those center faces around. My cube moves alone are not going to do that. So if I do a right move followed by a left move, that's not going to result in a full symmetry of the cube. So if I wanted to move these center around, I could use slice moves. These are these moves here, slice moves where I'm moving just the middle layer. And so using just the middle layer, we can move the centers around if we want. But those are not some of the moves that we put into Sage. We didn't put any slice moves in there. We just did these outside moves, these rights and lefts and fronts and backs. And so for that, it means that whenever I fix an orientation of the cube in space, blue top, let's say blue top, red front, yellow to the right, then my cube moves are always going to keep that orientation. Now, maybe it's worthwhile going back to, actually, I'll keep this one up here. It's worth back going to this and saying, okay, so the key observation is that I haven't fixed an orientation in space. If I'm dealing with the 2x2 cube and I want to sort of start to do an analysis of it, the problem is I could do rights and lefts moves and so on, just opposite face moves, and I can move whatever colors on top. And that's a problem in terms of counting. So what we could do is we could say, well, let's just fix a particular QB. I'm going to fix this corner QB, the orange, blue, and black one. And that's always going to sit in the back left corner. I'm never going to do a move that moves that one. The only moves I'm going to be allowed to do are ones that don't move that corner piece. So that means I could do front moves, I could do right moves, and I could do down moves. And those are precisely the three moves that keep the orientation of this QB fixed. And those are the three moves then we use to generate all of RC3. So these are precisely the moves that kept one piece fixed. I didn't have centers to keep fixed. So I picked a corner and said, let's fix that one. Let's not move it. And that's how we fixed an orientation of the cube. We got a frame of reference now. We imposed a frame of reference and everything was built upon that. Oval track puzzle. The slice moves are a combination of R and L. The problem is that the slice moves are a combination of R and L and a cube symmetry. So to do that slice move, I would have to do a right move. Sorry, this slice move here, which brings the red in between the two blues. So I would have to do a R move, R inverse, an L move, and then I'd have to do a full cube rotation to get to that position. So slice moves are combinations of R's, L's, and whole cube moves. So that's just one thing to keep in mind. Now we no longer have the blue up top. So if we're talking about doing the Sage analysis, we don't want Sage to tell us that this is not a solved puzzle. The red face being up is not solved. Much like it did with the 2x2x2 cube, it would tell us it's returning that this is not a solved puzzle when the black face is up. That's not solved. Why not? Because the blue sticker, which was 1, is now over here in whatever numbered spot that is. So Sage is going to tell us that this is not a solved puzzle, and it's because it's not detecting things up to symmetry. And so that's why we fixed an orientation. We fixed one corner QE, this back one, and we told it only use RD and F. And if you only use RD and F, you're never going to run into a situation where the whole black face is on top, because there's always that one corner QB, that back left corner QB that has the blue sticker up top, and it's never moving. So this is how we can account for Sage detecting that the puzzle is in a different orientation than it originally was, but yet it's still solved for our intents and purposes, but Sage would say it's not. So we can discount for that by fixing an orientation, fixing a frame of reference. What about the oval track puzzle? So the oval track puzzle is this one here. bring it back. It's 20 tiles. One of the moves we can do is just slide them along the track. That's a 20 cycle. The other thing we can do is we can flip the things that are in the turntable. That's the product of two cycles, the outer two and the inner two. And those are the two moves we need to generate the oval track. There's an oval track move and a turntable move, or a rotation and a turntable move. And so we can put that into Sage. We can say, here we go. Here's our one move, which we'll call R. There's our turntable move, which we call T. Let's build the oval track group, OT. And now that's all possible products of all possible inverses of all of these things. And now we can ask, how big is this group? Now, our query about how big it is, we can be a little bit more strategic in this. There's 20 tiles. So really the fundamental question is, are all permutations possible? How many permutations are there of 20 tiles? Well, there's 20 factorial of them. How big is our group? Well, that would be ot.order. So I really want to know, is ot.order the same? That's the double equal to. This is asking a question now. Are these two things equal to each other? This is a Boolean statement. Is it the same as 20 factorial? Let's execute. And it comes back saying, yep. Those are the same size. And that means that every permutation on the oval track puzzle is possible. All 20 factorial permutations. So there's no unsolvable configurations. So even if I could dump the puzzle pieces out and then stack them back in like we did with the 15 puzzle, it doesn't matter. We'd always be able to solve it. Boolean statement. A Boolean statement is true or false. So Boolean is a statement that is either true or false. False. And that's what this is asking. This statement is what we call a Boolean statement because it's asking the computer a question that it's either going to return true or false. If I wanted to know if they weren't equal, for example, I would use an exclamation mark and then equal to. And this is asking, is the order of OT, is that not equal to factorial? And it should come back saying false because they actually are equal. So let's, I'm just going to insert a new cell. And so we could ask things like, 2, is that equal to 2? And yeah, that's true. How about, well, let's say 2 to the power of 4, is that the same as 16? Yeah, that's true. Is 2 to the power of 4 equal to 15? Nope, that's false. So that's what we're doing here is we're just asking it a strategic question because we really just want to know if all permutations are possible. And this can tell us. Now we could do other things, right? I'm just going to copy and paste this code. And I'm going to change this to 19. And that means we're only using 19 numbers. And then I can ask it to, we'll call it OT19, just to be more specific here. And I'll load that in. And then I could do things like, okay, how big is OT19? Well, what's a good question to ask? What do you think? So I want to know what the order is. The problem is if I just ask for order and hit execute, I get this huge number. And that's not really helpful to know what the exact number is. I want to know what it's related to. So what do we think? 19 tiles. Yeah, we'd like to know, is it 19 factorial? And so we execute that and we get false. So it's not 19 factorial. So not all permutations are possible. So at this stage, what would be another question we could ask? Now we're trying to hone in on, okay, really, what are the permutations that are possible on this puzzle with only 19 pieces? Any ideas? We could factor it. Yeah, let's see what happens when we factor it. So we could go factor. And the problem is we get a lot of big numbers here, and so it's not really quite telling us. Ah, nice comment, Richard. Richard's talking about even. So if we look closely, we see that this is a 19 cycle. That's a cycle of odd length, so it's even parity. So that's an even parity permutation. This is also an even parity permutation. So we already know the generators are even. So the only chance we have of configurations are going to be the even configurations. We don't get all of the, the reason the factors are all prime is because when we do factor, it's a prime factorization. So that's what it does, is it factors it into the prime factors. That's what the term factor means. So we only have a hope of getting even permutations. So the real question is the number of permutations we get, or the number of configurations, is that equal to A19? So the alternating group of 19 objects, or in other words, just the set of even permutations. And we know that that size is 19 factorial over 2. So that's really the question we want to ask. Is the oval track puzzle on 19 pieces, is that equal to, or the number of configurations, is that only the even permutations? And yeah, we get that it is. So this says all even permutations are possible. Yeah, so exactly. So the idea is we now have enough theory to make us a little bit dangerous, right? We want to know, how do we, for 19 pieces on the puzzle, what are the possible configurations? Well, we know that the two generators, the two puzzle moves, are even. So worst case scenario, we can get all possible even permutations. There may be a subgroup of those, but we can't get any odd ones for sure. So we just query it. We say, can we get all the even ones? And the easiest way to do that to just say, do we get 19 factorial? So then you can now start to play with this. You could say, you know, for example, if I made this 11, so we had an oval track puzzle with only 11 tiles on it. And I'll change this to OT11. And I enter that. What would be the question I'd want to ask? How big is the oval track on 11 pieces? I'd like to know if all permutations are possible. But I already know that these are both even. So I'd have to look at factorial. But since both moves are already even, I'd have to say, well, I already know I can't get the odd ones. So I really want to know if I can get all the even ones. So factorial over 2, exactly. And yep, there we go. So on the oval track puzzle with 11 pieces, we can get all the even permutations. So those are the kinds of things we can do with this work with Sage. Is we can get it to answer some big questions that are quite tedious to calculate, but we can get it to do it for us. We just have to know what question to ask and how to interpret the answer. And in here, we had to ask the right question, and it had to do with our knowledge of parity of permutations, symmetric group and its size, the alternating subgroup and its size, so the group of even permutations, and so on. All right, so that's all I wanted to do with chapter 12, was just introduce you to the idea of the puzzle group, and then also that Sage can do some calculations for us. Now what I want to do is I want to get into the next section, which is chapter 13 on commutators. This is going to be how we build puzzle moves. So how to build useful moves. So if you're playing around with the Rubik's Cube and you're just like, I need to be able to move this piece here and that piece here and flip this, I don't know how to do that. This is the start of how you learn to build puzzle moves that do useful things. And it all starts with this definition of what a commutator is. So a commutator, the root word there being commute, so it's related to commutativity. Commuting means that the order in which you multiply doesn't matter. So in this case, we call the commutator of two elements of our group, G and H. We use square brackets to denote it. So this is the notation for a commutator, square bracket G, comma H. And what that is, by definition, it's just this product, G times H times G inverse times H inverse. So it's the product of all four of those elements, which involves the element itself and its inverse. Yeah, exactly. These are like puzzle cheat codes. Exactly. Commutators are the puzzle cheat codes. They're the things you're going to use to build moves on all these kinds of puzzles. So if G and H commute, then what happens? Well, if G and H commute, then I get G, H, G inverse, H inverse. But because G and H commute, it means I could always just switch the order around. Well, okay, if G and H commute, then G inverse and H commute and all that stuff, but maybe I'll work with the ones that we're stating. G and H commute, so I can switch those orders. So I can get this. And that would be the identity. And then I get H times H inverse, and that's the identity. So it reduces down to the identity. So in the case where you're in a group where the elements commute with each other, commutators are all just identities. So they don't give us any useful information. Commutators only are helpful in the case where your group is non-commutative, where there's operations or elements that don't commute with each other. So this is why you haven't seen the term commutator before. If you think back to all of your courses where you've done things involving a set of objects and operations on those objects, addition, multiplication, and so on, it always commuted. Multiplication of two integers, it doesn't matter which order you multiply them in. Addition of integers, doesn't matter which order you add them in. So you would never need a commutator because it would always just be trivial anyway. The first course that you probably would find use for it would be in linear algebra with matrices. Their commutators could potentially help you in understanding some structure of matrices. But that would be essentially maybe the first case you would even consider such a thing. Here, they're actually going to be vital because for our puzzles, our move sequences, it depends if you do one move followed by another word or another move or in the opposite order because they give you different things. So by the nature of our puzzles, move sequences are non-commutative, and so commutators are going to help us make sense of those. What a commutator actually does is it provides a measure of how much G and H actually fail to commute with one another. So the commutator, if G and H commute, it gives us the identity, but if G and H don't commute, then the resulting value is some measure of how much they don't commute by. In terms of permutations, if alpha and beta fail to commute with each other, then the commutator should be a permutation that only moves a small number of pieces, meaning that alpha and beta almost commuted with each other. There was only a few pieces that caused the problem and why they didn't commute. So let's get a feel for what commutators are and how to compute with them. So in this example, suppose we've got alpha is 1, 3 and beta is 1, 2, 3. The commutator alpha beta is alpha beta alpha inverse beta inverse. So that would be 1, 3, 1, 2, 3, 1, 3, and 1, 3, 2. So it would be that product there. And we could work it out and we get the value of 1, 2, 3. Let's double check to make sure this is the case. So if I just read along, where does 1 go to? Reading each factor one at a time. 1 goes to 3, which goes to 1, which goes to 3, which goes to 2. So 1 goes to 2. And that's what I have in my permutation. What does 2 go to? So reading along, 2 goes to 2, and then it goes to 3, and then it goes to 1, and then it goes to 3. So 2 goes to 3, and so on. So this is just an exercise of multiplication, but that's what it ends up being. We could do the commutator in the opposite order. The commutator of beta and alpha is this, and we could do that product. So beta is 1, 2, 3, 1, 3, 1, 3, 2, 1, 3. And if we multiply that out, we get 1, 3, 2. Does anyone notice something about these results? When I switch the order, yeah, they're inverses to each other. And so that's a result that I think I have you proving on the next assignment, is to show that if you reverse the order in which you do the commutator, you actually just get the inverse. So we'll just note it here as an observation. We'll say alpha or beta alpha is alpha beta inverse. So that's an observation. You'll prove this on the next assignment. So are these results from chapter 13 only applicable for puzzles with gaps? These results for chapter 13 are applicable to any group, and for puzzles without gaps, that's where we get a group structure on the puzzle. So the short answer is yes, they're only applicable for puzzles without gaps. The long answer is you can make them applicable to puzzles with gaps, like the 15 puzzle, and we will make them applicable in those cases as well. The subtle difference, and we've already seen what the gap can do, is on the 15 puzzle, notice there was a different solution criteria or solvability criteria. If the empty space was in spot 16, the permutation had to be even. But then depending on where the empty space is, the solvability flip-flopped. Whether it was odd permutation or an even permutation, it flip-flopped depending on where the empty tile was. And that's the kind of thing that happens when you have gaps. The gap causes a flip-flopping nature in the solvability. When you don't have a gap, things are a lot cleaner. Things are a lot cleaner in terms of the solvability criteria and how these techniques can apply. So what one could do to the 15 puzzle to make all of these results directly apply to it is to just say that you're only going to look at configurations of the 15 puzzle where the empty tile is in box 16. And that's it. And so then the solvability is just, it's only even permutations. And the set of all configurations of the puzzle are just the even permutations on 15 objects. So basically the puzzle group is a 15. But then you have to be careful how you deal with where that empty gap is. So that's the only consideration, is you can make all of these things work for puzzles with gaps. You just have to be careful about how to deal with the gap itself. So the short answer is, the reason I've introduced them here is because now we're just going to consider puzzles without gaps. And so all these techniques just apply quite directly and straightforward to those kinds of puzzles. Okay, so creating puzzle moves with commutators. Now what we want to do is we want to see why are commutators useful for creating puzzle moves. It's kind of a funny thing to make, right? You take two objects and you just multiply them together and then you tack on their inverses on the end. Why does that have anything to do with building puzzle moves? Well, I'll get to the main idea and then we'll prove it next class. But the main idea is as follows. There's a couple of things we want to know for puzzles. That is, if I have a permutation, what are the pieces that are fixed by it? We'll call this the fixed set. So those are the pieces that the move sequence didn't move, or in the context here, we're just talking about permutations. Those are the numbers that the permutation does not move. So those are the fixed set of alpha, is just the numbers that aren't in its cycle structure. Those are everything that goes back to itself. The moved set, on the other hand, are all the numbers in its cycle structure, because those are all the things that the permutation actually moves around. So that's what we call the move set. It's the complement of the fixed set, or it's the set of all things that where alpha of m is not equal to m, so that alpha is actually moved. So for example, if we're looking at A, which is the set of objects from 1 to n, and alpha is a permutation. This is before our example. This is one more object, and then we'll get to our example. Then what I'm going to do is for this set A, is I'm going to come up with a notation that talks about what alpha does to the elements of A. So this notation here, putting the permutation before a set, alpha A is a set, alpha is a permutation, all that does is applies the permutation to each element of A. Let's see how we can actually work with this in terms of an example. So let's first work with this permutation alpha. What's the fixed set of alpha? Those are just the numbers that alpha doesn't move around. So those are all the things that are left out of the cycle structure. Here we're in S13, so the numbers from 1 to 13, and I'm just going to list the ones that alpha doesn't move. So 1, it moves. Maybe the easier thing is to just also write down the move set and then go one at a time. 1, oh, that's something alpha moves. 2, that's not in the cycle structure, so that's something it fixes. 3, that's something it moved. 4, that's something it moved. 5, that's something it fixes. 6, that's something it fixes. 7, something it fixes. 8 is something it fixes. 9 is something it moves. 10 is something it fixes. 11 is something it moves. And 12 and 13 are things that it fixes. So that's what the fixed set is and the move set is. It's just those numbers for which alpha fixes and those numbers for which alpha moves around. That last definition is for a given set. So let's just let the set be 1, 3, 5, 7, 9, 11, for example. This notation alpha A just means take your permutation and apply it to each number in the set A. So alpha is a permutation, which means it's a function. So we're just going to apply it to each of these. And then we just write down the corresponding number. Alpha of 1 is 5, alpha of 3 is 3, alpha of 5 is 3. So that's back to itself. So alpha of 3 is 9. Sorry, not. Alpha of 3 is 9, alpha of 5 is 3, alpha of 7 is itself, alpha of 9 is 1, and alpha of 11 is 4. So that's all that notation alpha of A means. And with these things in mind, what we want to actually do is show that we can predict exactly what a commutator of two moves does. So what like an R move and an L do, R move and a U move. What do they do as a commutator? R, U, R inverse, U inverse. We're going to be able to predict what they move based on these kinds of concepts: fixed sets, move sets, and this set where we get the move acting on the objects in that set. So we'll get to that next day, and then we'll see that we can actually build moves on the Rubik's Cube. So I'll stop the recording here. My record button is not coming up. There it is. Stop.